Well, welcome to everybody who's joining tonight's meeting. I have to say I'm a bit amazed to find that this is actually the last of our guest talks for the season. You know, after the year we've had, I kind of thought the year might drag by, but this seems to have gone at some speed, and I am quite astonished to find we're there. Along, I think, probably with everybody else, hoping that by October, we will all be able to be in a better position and meet again and be able to all talk to each other in person up at the mills, and that would be just lovely, because not just for our society but for all the other societies that are struggling as well over the year. Our very last meeting is, of course, the Society's AGM, which is on the 25th of March, 2 weeks tonight. And I would encourage everybody who can to join in on Zoom. David will be sending out the links, because, you know, it lets you have your say, and everybody has a voice in a society, so it's worth joining in at the AGM. And lastly, if I can make a last request for any newsletter contributions to be sent to Jim Barber or myself. And I think Jim is hoping to get this newsletter out quite soon. And so if you have anything you'd like to send in, that would be smashing. And all of that lot takes us to tonight's talk, which is given by John Davies from the Royal Observatory in Edinburgh. And John is going to tell us about some absolutely fascinating missions to near-Earth asteroids, in particular the Hayabusa II and NASA's OSIRIS-Rex missions, which have carried out sampling of the asteroids for a future return of material to Earth, which makes them extremely exciting ventures. So if we're all set up and ready to go, I will just hand over to John so that we can hear some more about these really quite amazing missions. So John.
Righty-ho, here we go. Let's do, this is where we find out whether I really can share my screen. So you should see a title slide.
Yeah, that's good.
Okay, very good.
Excellent.
Right, so yes, hello everyone. My name is John Davies. I'm an astronomer at the UK Astronomy Technology Centre, the new name for the Royal Observatory, Edinburgh. I say I am an astronomer. I probably won't be much longer. I had my 67th birthday last month, so I'm pretty much past my sell-by date, but I'm still there at the moment. My background, I started life in, I've been to your society a couple of times over the last 20 years. And I'm sorry we can't meet in person, because I was looking forward to coming up to Dundee for the day, but never mind, these things happen. So my background, I have a degree in chemistry. I worked for a while as a flight test engineer on the Tornado aeroplanes you used to get flying out of Lucas. And then I went to I started doing astronomy part-time, and then eventually I decided that was more fun than working. So I got a permanent position in astronomy eventually at the ROE. And I've been there since 1987, modulo an 8-year tour to Hawaii. Now, my first job, which was at the University of Leicester, was searching the database of potentially moving objects detected by the infrared astronomical satellite in 1983. And that got me interested in near-Earth asteroids. That was what we expected to find. Actually, we mostly found comets, but NEOs are what we were supposed to be doing. And so I've been a solar system astronomer pretty much ever since, asteroids, comets, and Kuiper Belt things. So yep, today I'm going to talk about Hayabusa II and OsirisRex, and a brief nod to the DART mission, which was launched a couple of months ago, which is an asteroid deflection mission. So let's see, here we go. So you're astronomers, you probably know this stuff, but just to make sure we're all on the same page, let's ask ourselves, what do we mean by a near-Earth object, a near-Earth asteroid? Well, when I started in this game, asteroids were rocky and comets were icy. We don't think it's quite that simple anymore, but we also had these three classes of objects which crossed the orbit of the Earth, which came out of the main asteroid belt. So they were divided into three groups depending on how close to the sun they came. The green ones are the Amor asteroids. They have the aphelia is in the main asteroid belt, but they come inside the orbit of Mars, but they don't ever cross the orbit of the Earth. Then you have the Apollos, which were from the main asteroid belt inwards across the orbit of the Earth, and so were potentially Earth colliders. And you also have a small group of objects called ATENs, whose semi-major axis is less than 1, so they spend most of their time inside the Earth's orbit, and they can occasionally cross the Earth's orbit. Now, one thing it's pretty easy to figure out this. You can estimate the rate at which near-Earth objects crash into the Earth, and on that basis, the current asteroid population the lifetime of an asteroid in one of these Earth-crossing orbits is about 10 million years. Now, the solar system is a way lot older than 10 million years. So either there was a ginormous population of these things at the beginning, and these are just the few survivors we see, or there's some method for replacing them. Now, we can pretty quickly eliminate the ginormous population because it would have to be so huge, it's unrealistic. So what there must be is a way of refreshing this near-Earth asteroid population. So let me define something else, and that is what we call an asteroid family, what we call the asteroid distribution in the Kirkwood Gaps. So the vertical scale is the number of asteroids, and the the bottom line is the distance, typical distance from the sun, average distance from the sun. Now, you might expect this to be a smooth distribution, but it's not. What we see is several peaks with quite clearly defined gaps in between. And those gaps are called Kirkwood Gaps, named after Daniel Kirkwood, the astronomer who first noticed them. And the Kirkwood Gaps are caused because an object which orbits the sun at that distance has its orbit as a fairly precise fraction of Jupiter's orbit. So it goes around the sun once, goes around the sun twice, and suddenly it's back in the same relative position as it was to Jupiter a couple of years back. So Jupiter gives it a little tug. It goes around a couple more times, and it's back in the same relative position again, but gets another little tug. And pretty soon, these little tugs generate enough of a force to throw it out of the Kirkwood Gap and into the inner solar system. So that's why there are gaps. These are resonances with the orbit of Jupiter, in which objects are not stable because Jupiter's gravity flicks them in towards the sun. Now, that's jolly useful because the energy required to throw an object from the asteroid belt into an Earth-crossing orbit, if you do it in one kick, is quite a lot. In fact, it's quite enough to pulverize the asteroid. It would be very hard to knock asteroids intact from the main belt into the Earth-crossing orbits with a single collision. But if you have one that's orbiting near one of the Kirkwood Gaps, a relatively small collision can nudge it into the gap, and then Jupiter's gravity will fling it towards the Earth or into these Earth-crossing orbits. So that's how this population is renewed without the asteroids being smashed to dust in the process. And the other conceptual thing I want to introduce are what we call asteroid families. So this is another graph. This time it's orbital inclination against distance from the sun. And it's not random by any means. What we see is there are distinct clusters of asteroids which all have similar orbital inclinations and distances from the sun. And what we believe happened here is that a large asteroid is smashed up, and the bits of it stay in roughly the same orbit. And we call it an asteroid family, and we name each family after the largest known asteroid in it. So the Hungaria asteroids, top left-hand corner, are a family of objects created by the destruction of a much larger object. And the largest fragment that's left is the asteroid we call Hungaria. And similarly, the Flora family is 8 Flora is the largest of the asteroids in the Flora family. So that's why we call it the Flora family. So we have these two important concepts to deal with here. We have these Kirkwood Gaps, which throw things towards the Earth, and these families, which seems to suggest that asteroids go through periods of major collisions, which is enough to break them up and perhaps nudge them into a Kirkwood Gap. So that's what the near-Earth objects are, and that's how they get to be in the vicinity of the Earth. So let's look about how we go about exploring them. The first of these missions is so-called Hayabusa II. The clue's in the name. It's the second Hayabusa mission. There was a previous one about 10 years before this one, which was fairly successful. It rendezvoused successfully with Itokawa. it did do a sample grab attempt, but the sample grab didn't work very well. It also attempted to deploy rovers, but they didn't work. In fact, they didn't land, they missed completely. So the Japanese, and there were some technical problems with it bringing it home. So although they did get the capsule back, there was virtually nothing in it, just literally a handful of grains of asteroid material. So the Japanese took the lessons learned and said, well, we'll do it again and we'll do it better next time. And so they call this thing Hayabusa II, but it's virtually a clone of the first mission. The target selected for Hayabusa II is 162173 Ryugu. It's a carbon-rich C-type asteroid, so it's similar to the carbonaceous chondrite meteorites you find. It's what we call a potentially hazardous asteroid. So PHA is a name that's been developed in the last, I don't know, 20 years or so, and it means potentially hazardous asteroid. So it's an object which either crosses the Earth's orbit or could conceivably cross the Earth's orbit under the perturbations of Earth and Mars's gravity in the foreseeable future. It's about 900 meters in diameter, so a bit more than half a mile. It rotates in 7.5 hours. The other numbers are there if you are really interested. The Hayabusa II was an entirely, largely Japanese mission. It was a Japanese spacecraft. It was launched by a Japanese rocket from Japan. The launch vehicle is an H2. That's the picture of it down in the bottom right. And as we'll see with some of these other missions, it does not fly directly to the asteroid. In fact, what it does is it goes around the sun once, re-encounters the Earth about a year later, and then uses the Earth's gravity to fling it out into an orbit which brings it into rendezvous with the target asteroid. This is increasingly common in planetary exploration these days. It's a way of getting more spacecraft to where you want to go without having to use so much fuel. And the European mission to Mercury has about 8 of these Mercury flybys before it finally goes into orbit around Mercury. So this idea of using swing-bys to use the Earth's gravity or some planet's gravity to send you to where you want to go is increasingly common. So it's launched in November 2014, and it arrives for about 4 years later, in 2018. And when it gets there, it parks itself in what the mission team called the home position. Now, this was a position about 20 kilometers away from the asteroid, and it's essentially it's in orbit around the asteroid, but the asteroid's gravity is tiny, so it's more or less flying in formation rather than being in orbit. It sits there at 20 kilometers. It watches the asteroid rotate underneath it, so it can take lots of pictures. And from time to time, it drops its altitude so it can take high resolution pictures. So rather than having a zoom camera, they just basically take the spacecraft closer to the asteroid, take some pictures, and then back it away again. So the picture on the left shows you what the asteroid looks like. Generally, it's not round. It's a kind of diamond shape. It has an equatorial bulge. It has some quite large rocks on it. You can see in the bottom center, there's a very large rock right there. But if you get in closer, and the right-hand picture is a high-resolution photograph with a scale bar showing a 1 meter, that's 3 feet. So the surface is covered with 3-foot sized boulders, and it's covered, and it's like this everywhere. It's not just an odd boulder field. The surface is very, very rocky, very, very rocky. The albedo, the reflectivity, is about 4.5%. The reflectivity of coal is about 15%. So this is darker than coal. And from the orbital characteristics and the volume of the asteroid, you can determine from the photographs, it turns out that it must be a rubble pile. So it's about 50% void. So although it looks like a solid object, it's got a lot of holes in it. It's more like Gruyere cheese or something like that, with lots of boulders with lots of holes in between. It also has many critics suggest that it's been heavily bombarded in its history. So it probably formed more or less as it is in the main asteroid belt, and then was subsequently pushed into an Earth crossing orbit, presumably via one of these interactions with a Kirkwood gap. So having mapped out the thing, they then start on the first stage of their mission, which is to drop a series of landers onto the surface. There were Japanese landers were called Minerva, and the Mascot lander was provided by the French Franco-German collaboration. So let's look at the Minerva landers first. It's called Minerva II because there was a Minerva I was on the Hayabusa 1, and this is Minerva II-1 because there are two kinds of landers, although in fact Minerva II-2 failed and wasn't deployed. There are two Minerva II-1 landers. They are 18 centimeters in diameter and 7 centimeters tall. That's about the size of a sponge cake. You know, it's a bit smaller than a dinner plate. So they're not very big things, and they only weigh a kilogram. They are sometimes called rovers, but they're really hoppers. They each have inside them a device which is not dissimilar to the vibrator in your mobile phones. And the gravity on the asteroid is so weak that simply turning on the vibrator is enough to make the little spacecraft jump up into the air, to vacuum, of course, but jump up off the surface and land randomly somewhere else. And their surfaces are covered in solar panels, so they generate electricity on principle. They can survive for quite a long time. So the next picture is some of the images taken by these landers. They're both pictures from Rover 1B. They're somewhat difficult to interpret because despite the fact that I have searched repeatedly and even mailed the Japanese Space Agency, I've been unable to get any copies of these pictures with scale bars on them. So I don't really know how big these stones are. I'm guessing they're sort of oranges up to television sets kind of size, because we know the surface of the asteroid is covered in meter-sized boulders, and certainly even at close range you can see it's very, very rocky surface. Rover 1B, which is the one that took these pictures, returned 39 images over a period of 10 asteroid rotations. If you remember, the asteroid rotation period is about 7.5 hours. So that's 3 Earth days. Its brother, Rover 1A, was rather more robust. It lasted 36 Earth days, 113 revolutions of the asteroid, and it returned 609 images. I don't have any scientific results on these. I don't know what they carried apart from cameras, but because they were fairly simple landers. A somewhat more complicated thing is this. It's called the Mobile Asteroid Surface Scout, or Mascot. This is the lander provided by this German Space Agency and the French Space Agency. Now, Mascot is bigger than the Minervas. It's 29 by 29 by 20 centimeters. So that's about the working volume of a microwave oven. You could put it in your microwave, but it probably wouldn't rotate because it would hit the sides as it tried to rotate. So we're talking about something a bit bigger than a shoebox, but not much bigger than a shoebox. And this weighs 9.5 kilograms. It's just like the Minerva landers, it is simply dropped. There's no retro rockets or anything complicated like that. The gravity of the asteroid is so weak that you simply go down near the surface and just let it go and allow it to fall, and it doesn't accelerate enough to do any damage when it lands. So through the miracle of modern technology, those of you who are my sort of age will remember these missions like Mariner and Pioneer, where we were lucky to get about a handful of pictures back. These days, video cameras are so cheap and so easy to install that you get fantastic pictures of almost every aspect of the space mission these days. So this is the Mascot lander, having been released from the mothership at an altitude of 51 meters. So that's what, about 170 feet. And it takes 6 minutes to fall 50 meters. And when it finally reached the surface, it bounced around for 11 minutes. The gravity is so weak that even though it lands at a very low speed, it can easily bounce up again. It actually landed upside down, and it had a little flip arm that was popped out and caused it to move itself the correct way up. Now, the Mascot had no solar panels. It was purely battery powered, and it survived on the surface for about 17 hours, which was the design lifetime. I think the next picture is some pictures. Oh yeah, so here we see it coming down. I've got a crib sheet, but it's not completely up to date. So the picture on the left in the blue square, you can see the shadow of the Hayabusa spacecraft itself and its two solar panels sticking out on either side. And then if we zoom in on that blue box, you can see the Mascot lander itself in the top left-hand corner, just a single white dot. And you can also see the shadow of the Mascot lander as it falls down to the surface. Isn't that just incredible? Like I say, if you think back to the days of Surveyor on Viking, you know, this kind of quality of pictures is just unreal. So here's a picture from the surface. This one does have a scale bar on it. You see it says 5 centimeters, that's 2 inches. And this is a picture taken on the night side of the asteroid. That was taken during the night phase of the asteroid. There were some thermal instruments which measure how quickly the asteroid cools. And they show that it has, I've got to get down, I always struggle with this, it's high thermal inertia. So it heats up slowly and it cools down slowly. Now rocks have low thermal inertia. They heat up quickly and they cool down quickly. So the fact that this heats up slowly and cools down slowly tells us that the surface has got lots of voids in it. So it's highly porous. Those lots of voids, it makes it difficult to conduct heat. So it's very powdery with again low strength and lots of little gaps in between the grains. But the main event was these so-called touch and go missions. These are to collect samples. And the way Hayabusa does this is it lowers itself down onto the asteroid, and projecting from the bottom of the spacecraft is a large, for lack of a better word, I'll call it a trumpet, a large trumpet. And the idea is that the spacecraft lowers itself down to the surface of the asteroid, and just as the trumpet hits the ground, a ball bearing, a little bullet, is fired down the trumpet into the soil or into the dust. And the idea is that this will kick up dust, which will bounce up the trumpet, and so be captured by the sample return mechanism. And this is what went wrong on Hayabusa 1, because they did the touch and go all right, but the ball didn't fire, the bullet didn't fire. And so virtually no material was flicked up into the collecting sample. The little thing off to the left, the little round thing that looks like a Coke can or something, is a device dropped by the satellite to help it navigate down to the surface. Although this is not that far away from the Earth, it's too far away to control the thing in real time. So the whole thing has to be pre-programmed. You can't fly it down with a joystick because the radio signals take too long to get there and back. And that little target marker is just there to help the Hayabusa navigate down to the surface at the correct speed. So let's see what happened when they did it. This is what the target area looks like just before the touchdown. Now the second picture, which shows after the touchdown, is slightly offset. But if you see that rock in the bottom slightly left of center, which is split into 3 pieces, that same rock will appear slightly further up and to the left in the following image. So that's the sampling area before the touchdown, and that's the sampling area after the spacecraft starts to back away. And there's that 3-piece split rock on the left-hand edge of the picture. And you can see that during the sampling experiment, material has clearly been flung about because there are all these dark rays and shadows that weren't there before the touchdown attempt. So they knew that the first sample attempt had been fairly successful. There is a video of this, but bitter experience has shown me that showing videos over Zoom is a mistake. But when it does do the sample grab, all heck breaks loose. Stuff flies in all directions for a few seconds. So there's clearly material flying around, both from the bullet that's fired into the surface to kick up the dust, and also from the thrusters as the spacecraft starts to back away again. And the shadow, the picture of the spacecraft is its own shadow projected onto the surface. So all well and fine. We've got ourselves some dust from the surface of Itokawa. But there's an issue here, and that is that we have come to learn over the last 30 years or so of a process called space weathering. So I remember this coming up when I was a lad, so to say. and it was just starting in this field. It was highly controversial. The argument was that what we see on the surface of an asteroid, which of course is what reflects the sunlight and therefore what we detect from our telescopes, is not necessarily pristine surface. It's been cooked and baked and shone on by the sun and by cosmic rays for thousands, if not millions of years. So maybe the surface of the asteroid is weathered by the sun having shone on it, faded, baked out. And the way of testing this is to get a sample from below the surface. And this is how they decided to do that. The Hayabusa carries on board a thing called the small compact impactor. That's this thing which is shown in the bottom left-hand picture. And it's released from the mothership. The mothership then runs around the asteroid and hides around the back. You can see it hiding in the bottom right-hand corner of the right-hand picture. And once Hayabusa is safely tucked away out of sight, a explosive charge in the SCI hurls a copper plate at the surface and punches a hole through the dust and hopefully creates a crater. And that crater samples or exposes material that hasn't been baked by the sun for millions of years. So the idea is then you go down a second time and sample material that's not been exposed to the sun. To see if it works, they deployed a free-flying camera. That's the thing in the sort of top right-hand corner with the, looks like a Coke can with a pencil sticking out the back. That's just a small digital camera with a 3-hour lifetime, whose only function is to try and observe the impact. The compact impactor contains what's called a shaped charge. So the shaped charge is a bit like the warhead of a bazooka. People found out quite a long time ago that if you shape your plastic explosives like in a cone or a cup, all the blast goes in one direction. So they shape the charge so that all the blast goes in one direction and flings this copper plate straight down to the surface. So the explosion does not occur on the asteroid itself. The explosion occurs in the impactor, or the small compact impactor experiment, and it's that explosion which flings the copper plate into the surface. So the only thing that happens on the surface is just the mechanical impact of this piece of copper. Now, it all sounds great in theory. How did it work? Well, here's the small compact impactor released from the mothership, and these are some pictures from the little relay camera. The bottom picture is the sort of general view, and the top picture is the magnified view. And you can see in the top picture, you can actually see the material being thrown up as the impactor itself strikes, the copper plate strikes the asteroid surface and punches a crater. So we know that that worked. Then the navigation team had to go back and find the crater. So they went back and they looked all around where the impactor was expected to have landed until they found something that had changed in the last few months. And here it is. Here's the before and after pictures. They're pretty well aligned this time. You can clearly see the picture on the left has this sort of triangular rock just off to the top right. And on the second picture, there's a big crater right next to it, which wasn't there before. So that's where the copper plate smashed into the asteroid and exposed the surface. So now all you have to do, he says, all in a sort of affable way, is go down and grab a sample. So the technique is exactly the same. The Hayabusa lowers itself down. Here it comes. There's the bottom end of the trumpet, just about to push itself into the dirt. And I say again, if you go to the JAXA website, you can see this in video, but I'm not going to show a video. Just going to show a single frame from it. Here's what happens when it hits. Right, stuff flies everywhere. Dust, rocks thrown up by the thrusters, and the sample probe pushes itself into the dust, and stuff bounces up into the horn for collection. Great, so mission accomplished. There was actually enough resources on the spacecraft for a third attempt, but they were pretty confident they'd got a decent sample from the first 2 attempts, and rather than risk everything on trying to do it again, they decided that they would quit while they were ahead and stop the sampling and then bring the spacecraft home. So what do we learn from all of this? Well, the mothership had a bunch of cameras and spectrometers and stuff. And they produced this model after which Ryugu was formed. It began its life in the main belt in a much larger asteroid. That asteroid was large enough to have some sort of internal heating, which caused chemistry to take place. So there was aqueous alteration. So aqueous is just water, right? So this is what we see when we get water reacting with minerals. It changes the composition of the minerals. It doesn't mean there was necessarily, not suggesting there was liquid water, but there was enough water molecules trapped in the dust and enough heat to allow chemistry to take place. Now that heat probably came from trapped 26 aluminum. This is a radioactive material formed in supernovae. If it gets incorporated into a body and then decays radioactively, it generates a lot of heat, and that heat melts the inside of the object. That's why the Earth has a molten core, because a lot of aluminum 26 was trapped in the Earth's core, and when it decays, it heats it up and causes all the iron to melt. It is possible to heat it by bashing into the outside, but it's pretty hard. You have to smash into it pretty evenly and all over the place to get a decent amount of heat smoothly distributed through the interior. So it's most likely this aqueous alteration occurred as a result of trapped aluminum isotopes. At some point later on, the parent body was struck by another asteroid, and that impact was hard enough to smash the parent asteroid into many, many pieces. So that's, if you remember, I said that's how we form these families. The parent body is smashed into many pieces. They don't travel very far apart. In fact, they're mostly loitering in the same bit of space. And in fact, there's a good chance they'll bump into each other. So some, at least, of these fragments then start to bump into each other and reassemble themselves as an intermediate body. Now, we don't know exactly how many times it's happened. It may have happened more than once, but let's assume, for the sake of argument, that it forms this intermediate parent body. That is in itself then hit by yet another small asteroid. After all, it's still in the asteroid family. There's still lots of pieces around, which breaks it up again. And once again, these fragments gradually coalesce into a smaller object. And that object is Ryugu, and that's the object that finds its way into the inner solar system. So that explains how we can get aqueous alteration in a body which is far too small for it to occur naturally. It also explains why the object is so fragmented. There's so many boulders on it, why there's so many voids, because it's not a solid object at all. It's the result. It's a bag of marbles held together in a net, in an onion net or something. You know, it's a lot of small pieces that have been broken apart and reassembled, possibly more than once. So that's how we understand that Ryugu formed as it is. So the mothership, it has its ion engines, and at the appropriate time, it turns on its ion engines and heads back to Earth. So it left the asteroid in November of 2019, and a year later, it approaches the Earth. The sample canister, which is a little Apollo, looks a bit like an Apollo capsule on the side, it's only the size of an ice bucket, has its own heat shield. It is on a collision course. It's put on a collision course to the Earth by the mothership. The mothership then fires its thrusters to change its course so it doesn't crash into the Earth's atmosphere, and only the sample return canister comes down. And here's a picture of it landed in Australia in the Woomera missile range. What's that? 2 years ago now. And here's a picture of one of the recovery crew with the sample return canister. And here are these samples. Now, I don't know about you, but my first reaction when I see all this is, my gosh, didn't they get a lot? But if you actually start to read the text a bit more carefully, you find that the total mass collected is of the order of 5 grams. Now, I don't know about you, I don't really think in grams very easily, but 5 grams is about a biggish licorice allsort, a couple of sugar cubes, 1, maybe 2 cocktail olives. You know, we're not talking about a huge amount of material here. It's a teaspoon of salt, basically. That weighs 5 grams. However, the chemistry of it seems to be typical of the bulk material of the asteroid, so it does seem to be a fairly representative sample. It's slightly more smashed up. The ratio of big pieces to little pieces is slightly implies it's slightly more smashed up than the asteroid itself. But hey, it's been smashed. It's been crashed into and grabbed and flown back to Earth and re-entered, so that's maybe not surprising. So it's slightly more fragmented than the typical bit of asteroid, but not by much. So then they divided up the, remember they've got two samples. There's the before impact, which is surface, and then there's some stuff that's been excavated by the impact experiment. They took out a few of the larger fragments and then divided the rest of up. Again, when you look at this picture, it looks like quite a lot, but you see each of these sample containers is generally contains less than a gram of material. And for scale, well, that's how big those containers are. It's really quite a small amount of material. However, you've got the material back to Earth, and with modern mass spectrometers and non-destructive techniques, geologists can learn an awful lot from literally a single grain of dust. So there's a potentially huge amount of science to be done on these samples. Still to come, the mothership is still intact. It's still working. It flew safely past the Earth, and after a lot of thinking, the Japanese have come up with a rather complicated extended mission. The first thing to do is to retarget to another asteroid. It's the same sort of size as Hayabusa. It's about a kilometer, as Ryugu. It's about a kilometer in size. That's what it's called, 98943. It's about the size of a mountain. And if all goes well, they should fly past that in July 2026. Now, they cannot do any more sampling, but of course, all the cameras and spectrometers are still working. So they should be able to get a decent scientific return of the fly past. And then, after returning to the Earth a couple of times to make more gravitational adjustments to the orbit, the final objective is to rendezvous with this thing, 1998 KY26, which will hopefully have a chassier name by then, in another 10 years. It's almost 10 years away. KY26 is a very small asteroid. It's only about 30 meters across. It also rotates very quickly, 11 minutes. Its spin period is 11 minutes. Now that's telling us something, because we have known for some time from ground-based observations that small asteroids don't rotate very quickly. There's a sort of upper limit of rotation of about 2 hours. Once the rotation period goes faster than 2 hours, there just aren't any small asteroids that rotate in less than 2 hours. And that's because, like Ryugu and Itokawa before it, they're rubble piles. And if you spin them too quickly, they just fly apart. So the only way you can get something to spin faster than a couple of hours is that if the object is not a rubble pile at all, but a single boulder. So KY26 is probably a single shard of rock, essentially a skyscraper-sized rock, which is rotating. And because it's a single piece, it has a lot of structural strength, so it can rotate quickly. So, well, we'll see. Hopefully we'll all be still around in 2031, and we'll see what we see when it gets there. So there's still a lot of science to come from Hayabusa. Firstly, from the lab work on the samples, and secondly, from these extended mission flybys in the next 10 years or so. So let's move on to the other mission, OSIRIS-Rex. This has the most incredibly convoluted acronym you can think of. It's part of the NASA New Frontiers program. The security bit is to do with the fact that it's part of the NASA program for Earth defense against asteroid impacts. So they need to understand near-Earth objects so we best know how to deflect them should we ever need to. Was selected, as it says, in May 2011 as one of these New Frontiers missions. The Pluto flyby was one of the New Frontiers missions as well. And its objective is very similar to Hayabusa, except it doesn't have any rovers. Go to the asteroid, rendezvous with it, park yourself in orbit, grab a sample, and bring it home. And you can see from the picture size of this thing, some people standing around it. before it's put on the rocket. The target is an asteroid called Bennu. It's another carbonaceous, carbon-rich, primitive object. Also potentially hazardous asteroid with a low possibility of striking the Earth sometime in the next 200 years. It's 500 meters. It's half the size of Ryugu. If I was physically with you, which I had hoped to be, I would at this point be passing around my 3D printed model to show you what it looks like. It's another one of these diamond-shaped objects. 500 meters, less than half a mile across, rotates in 4 hours. And OsirisRex arrived, and it made several flybys to get the general gravitational field and to take some global mapping. And what you see is exactly the same as you saw at Ryugu. The whole object is covered with boulders. Some of them are very large. There's almost no flat, dusty surface anywhere. And this was not predicted by either the thermal models. Now, I used to do asteroid thermal modeling, so I guess this is partly my fault. This surface was not predicted by either the thermal modeling or the radar observations, which were made from radio telescopes like Arecibo. So this was a bit of a blow because the sample mechanism was working on the assumption that they would find some nice flat dusty places where they could land. Here's what it looks like as it rotates. You'll see some of these boulders are very large. In fact, they're large enough that they started to give them individual names. And then there was no naming convention. There's a name. I've got a message that says move on because I suspect it's using too much system resources. There's a naming convention for craters, there's a naming convention for mountains, there's a naming convention for valleys. But there's no naming convention for big stones. So they had to invent one, and they eventually decided if the stone was more than 5% of the diameter of the object it was sitting on, you could give it a name. And that name would be something with the word saxum, saxum being the Latin word for stone. So some of the largest stones, larger boulders on these asteroids are given individual names. And here's a typical one of them, 7.5 meters. That's about the size of my house. And again, you see the whole surface is very rough, and it's also quite homogeneous. It's not all the same color. It's not only lots of pieces, but it's lots of pieces of different colors and shades. This was the big news early on. During some of these close flybys, what they detected was material being ejected from the asteroid. Now, the principal investigator said this was the biggest surprise of their career, and I completely agree. No one expected it. I mean, comets, you expect it. You expect comets to outgas, you expect comets to squirt material into space, but this is a rock. Well, actually, it's a pile of small rocks. But this isn't a fluke. There have been several of these episodes seen by the spacecraft. So this isn't just some random chance. It's not just one meteorite that just happened to hit on the day we were there. This seems to be a regular performance. Some of the material falls back onto the surface. Some of it goes into orbit. Some of it's actually ejected into space. So one day, should this thing's orbit change to bring it close enough to the Earth, we may form a meteor stream from this material ejected from Bennu. The size of the dust stuff that's coming off varies from about sand grains to oranges, pebbles, cobblestones, that sort of size. We're not talking about huge things, but it would make quite a decent meteor shower if the Earth ever intersects it. What is happening? Well, several possibilities. One is trapped gas, but that's unlikely. One is meteorite strikes, but it's happened several times, and it's not likely there would be multiple meteorite strikes so close together. And the other hint is that these things always seem to happen at locally 3 o'clock in the afternoon. So it's 3 o'clock in the afternoon on the asteroid. So the sun's passed overhead and it's halfway down to setting. So what's probably happening is that the asteroid is getting heated up by the sun. The heat is soaking into the rocks, and then as the sun starts to go down, the temperature starts to drop. This thermal contraction of the rocks, which maybe cause the rocks to go ping and start to eject material. That I think is the smart money as to what's causing this. It's thermal expansion and contraction of the rocks, causing the rocks to shatter. They also find, I said a little minute ago that these things, the sample, the surface of rocks are different colors. In fact, some of these things are very different colors. And these are most likely actually meteorites. They're essentially meteorites. They're material ejected from another asteroid at some point, which has landed on Bennu and has sat on the surface ever since. So let's talk about the sampling. This is a diagram of the spacecraft. I couldn't even begin to tell you what all of those acronyms stand for. Oh, optical visible infrared spectrograph is one of them probably. The important thing is this thing called TAGSAM, which is the trombone sticking out to the bottom left-hand corner. It's the touch and go sampler. That's the thing that's going to try and grab the sample. It's what it looks like in real life. There's a person in a clean room with a mask. It's probably not a COVID mask. It's probably a clean room mask. So you can see the size of this sampler. It's a bit bigger than, it's about that sort of size. And it's on a long arm. Now, the first problem the team have is they have to find somewhere on the surface which is smooth enough to make this sample. Remember, these spacecraft have big solar panels sticking out, so they can't go anywhere which has a lot of large rocks in case the solar panels hit the rocks on the way down. The original plan was they would need a flat surface 10 meters in diameter. Luckily, the engineers who controlled the spacecraft figured out they could do it better than they thought, so they were willing to relax the flatness criteria a bit and reckon they could still get down safely. They identified a number of potential target sites which had 10 or 20 meter flattish areas. And then they investigated each one in excruciating detail. And again, if you're interested, go to the OsirisRex website. You can download hundreds and hundreds of pictures showing these things. The one they chose is the one called Nightingale, which is in the top left-hand corner of this set of 4. All of these target areas are named after birds. So Nightingale is where they go. And the sampling approach is very similar to Hayabusa. You drive down to the surface, you put your trumpet, you push your trumpet into the surface, but instead of firing a bullet, you actually fire a blast of nitrogen gas. And the nitrogen gas stirs up the dust and hopefully blows some of it into the sample horn. Now, I did say I wasn't going to show videos. This isn't a video, this is a GIF, an animated GIF. So we'll see the spacecraft arm going down. At the last minute, it makes last second, it makes an adjustment so that it hits the surface perpendicular, and then you'll see what happens. So down we go, still pretty rocky, last minute adjustment coming up, wham, and stuff flies everywhere. So that's both the probe driving itself into the surface dust and the thrusters firing to back the spacecraft away, and material flies, as you can see, flies everywhere. Now, you may have heard after the sample grab that there was concerns that the sample was leaking out into space. And it's only 3 pictures. It's just an animated GIF again, showing material which is actually escaping from the sample head. And now I struggled a bit to understand what was going on here until I found an explanation of it. So this is what happens. The TAGSAM goes down. If we look inside it, what's supposed to happen is the nitrogen gas blasts down the outside. It then blows some of the material up, and as it lifts up, it blows open those red doors, and those red doors allow the dust to be accumulated in the sample container. Now, those red doors are then supposed to close again when the nitrogen stops puffing. But what seems to have happened is that several large pebbles were blown into those doors, and the doors jammed open because there were pebbles in the way that stopped them closing properly. Now, it's a measure of the cleverness of engineers that the original plan was that they would measure how fast the spacecraft would rotate, its moment of inertia. Then they would do the sample grab, and then they would measure its rotation inertia again. And by the difference in those rotational inertias, they would deduce how many grams of dust they'd picked up. Now, I mean, it's just mind-boggling to me that you could even begin to think of doing it with such precision, but that was the plan. However, because they knew these doors were open, or partly open at least, they were worried that spinning up the spacecraft might spin up, throw out even more of the sample they've gone to so much trouble to collect. So they didn't do that. They said, well, we'll just assume we've got plenty and we'll park the sample container. And these are not artist impressions. These are not pre-launch things. These are actual photographs from the spacecraft. So what you see here is this thing, the sample head, which looks a bit like a car oil filter or something, being positioned above the re-entry capsule. It's pushed into the re-entry capsule and then latches in place. Once it's firmly latched, the sample arm is detached and withdrawn out of the way, and then the clamshell closes to protect the sample mechanism in the re-entry capsule. The spacecraft was then allowed to drift away. That's mission accomplished. So it was then allowed to drift away, but after some thought, they decided they would go back one more time and make another flyby and try and image the sample site. So this is the area where the sample was taken. And what it's showing you is that a largish boulder, which has got the circle in it, is flung downwards and outwards during the sampling. So the X is where the sample mechanism hit. And the thing in the ring is a largish stone, which is thrown some distance by the sampling mechanism. So remember, the gravity is very small here, so it doesn't take much to move something. But even so, it's quite impressive that they can find individual boulders that have been shifted around by the sampling. How are we doing for time? Yeah, fine. So here's the plan now. The spacecraft OsirisRex, there was enough gas for several attempts, but they were pretty convinced they got more than enough on the first attempt, so they decided not to try again. The spacecraft was commanded to leave the asteroid in May of 21, so that's 18 months ago now, I suppose. No, 22, isn't it? So it's 8 months ago. It's scheduled to return to Earth in September of 2023. And the plan is much the same as it was with Hayabusa. A few hours before the spacecraft reaches the Earth, it's heading straight for Earth. It releases the sample return re-entry vehicle. It then fires its thrusters to move itself away so that it doesn't crash into the Earth, and it goes into orbit around the Sun. The sample return capsule has its own heat shield like an Apollo, comes through the atmosphere, pops a parachute, and then lands in the Utah desert, either to be snatched by a helicopter or to be picked up from the ground after the touchdown. And that all happens, hopefully, in about another 18 months. They think they've got a much larger sample than the Japanese mission. They think they have at least a kilogram, possibly a kilogram and a half of material. So there's a treasure trove of stuff there for the people in the labs once they get it back. So just to finish off, just 4 or 5 slides now to talk about this other near-Earth asteroid mission called DART. And DART is the Double Asteroid Redirection Test. DART is not a scientific mission per se. It's part of NASA's planetary defense program. And the question that it's trying to answer is, if we knew that an asteroid was going to strike the Earth in the near future, what would we do about it? Do we get Bruce Willis and an atom bomb, or is there a different way? And the problem is, nobody really knows how an asteroid will react to being smashed into by some sort of deflection mechanism, whether it's an atom bomb or something else. So they said, okay, let's try it. We know from Hayabusa II, OSIRIS-Rex, and a couple of other missions that these asteroids are rubble piles. And so just smashing into them might not produce the effect you want, because it might just break them up rather than change them. But there's only one way to find out, and that's to try it. So they devised this mission called DART. And the target of DART is an asteroid called Didymus. Didymus is another Earth-crossing asteroid. It goes around the Sun every couple of years. Its closest approach to the Sun is about the Earth's orbit. Its most distant point is out beyond Mars. It is not currently on an Earth colliding orbit, nor is there any danger that the DART spacecraft will push it onto one. But it is an interesting test case for a reason which I'll explain in a second. This is the reason it's interesting, is that it's not a single object, it's a binary. So Didymus itself is the big thing on the right, 780 meters in diameter, so halfway in size between the two we've been talking about all evening, bigger than the Eiffel Tower. But it has a satellite of its own called Dimorphous, which is much smaller, about the size of the Statue of Liberty. And Dimorphous orbits Didymus. Okay, strictly they go around their common center of mass, but pretty much we can think of a Dimorphous as going around Didymus. And we can measure the orbital period very accurately from the ground because it's an eclipsing system. The little asteroid passes directly in front of and directly behind its parent. So you can time the crossings very, very accurately, get the orbit very, very accurately. So the plan is to smash the DART spacecraft at about 6 kilometers per second directly into Dimorphous, the little one. And that impact should occur on the 26th of September this year. And the expectation is that that impact will change the orbital velocity of Dimorphous around Didymus by about 4 millimeters per second. Now, you might not think 4 millimeters per second is very much, but it's actually quite a lot because it's not going to take very long for that to make a noticeable change of the orbit. The DART spacecraft is quite small, but it's traveling pretty quickly. It has only one side, it has only one instrument, and that's a camera. It has no scientific instruments at all, it just has it's a camera. Because as with the sample returns, this is happening too far away for real-time control. The Didymus is tiny. So the job of the camera is, as it approaches the asteroid, it has to find it, resolve the satellite, figure out where the satellite's going to be, and then alter its own trajectory so that DART smashes into Dimorphous at this very high speed. And that all happens in the space of an hour or two. This is not something which happens over days. They detect it a couple of hours before the collision. I mean, they know where the system is, but to actually get a precise location for Dimorphous to crash into it, they've got to do all that in an hour or two. And this is the spacecraft. That the camera is the big orange pipe on the right-hand side. That's all there is to it. It's just a motor and a camera and a small secondary payload, which will be ejected just prior to the impact. It's an Italian CubeSat, which will hopefully return photographs of the impact itself, as the CubeSat will be released just before the impact, so it will fly past. It will fly past rather than collide. Here's an artist's impression of it all happening. So we see the main spacecraft smashing into Didymus, blowing a crater and hopefully changing its orbit. The little Italian CubeSat is slipping away photographs in the background, and the whole thing's being observed by ground-based telescopes, because it's the ground-based telescopes which will tell us how successful this has been. If we simply threw DART at a regular Earth approaching asteroid, it would be very hard to figure out what change had been made, because the orbital change is very small. There are lots of other things going on, solar wind and so on. But by targeting a binary and hitting the satellite, it's very easy to measure the effect, because we can measure the times of eclipses very accurately. And this is some predictions of what will happen after the impact. So the black line is what the light curve looks like before anything happens. If you hit it hard enough to change the orbital period by a minute or so, after a week or two, you see the red curve, which is clearly displaced from the black curve. And if you manage to change the orbital period by 7 minutes, you get the green curve, which is even more easily detectable. I mean, that's only a week after the impact, and you're already seeing a huge change in the light curve. Now, ground-based astronomers can measure these sorts of things very accurately. So the ground-based team will be able to establish quite quickly how much of an effect the impact has had on the orbital period and how much it's changed the orbital velocity of the satellite. And that will all then be fed into models of how we might deflect a near-Earth asteroid should one be found in the future, heading directly for us. The current orbital periods are just under 12 hours. They expect the impact will change the period by about 10 minutes. And we can detect that a 10-minute change in a 12-hour period very, very easily. And that's the end. That's all I really wanted to say. I've been going for just a little bit under an hour, which is about as much as I think most people can put up with. So I will stop the share. And if you have any questions, I'll do my best to answer them.
John, thank you so much. That is just simply fascinating, and an astonishingly clear presentation as well. I'm still getting my head around the clarity of these images, which is mind-bending.
It's truly fantastic, isn't it? I mean, I grew up with, I don't know, Surveyor, I suppose, and Viking, where it took half an hour to get back a single picture, and now there are literally thousands of pictures on these NASA websites of these asteroids, right down to the millimeter scale. It's fantastic.
Sitting here looking at distinct little bits of rock on an asteroid is quite tough to kind of grasp, really. They are fabulous.
Yeah. I mean, Brian used to work at the observatory. You'll know what I mean by this. I used to observe these objects, and the whole object, the whole asteroid, was a single pixel.
Yeah. I always put it when you see the shadow. You showed some of the images of the shadow of the craft as well. That makes it realistic. It's like the Ingenuity helicopter on Mars. When you see the videos of that, and you've got it flying, and you've got the shadow of it moving, which is somehow that adds to it as well. It makes it seem so much more real.
Yeah, I mean, people talk about the scientists who do this stuff, because a lot of it's not scientists at all. It's engineers who do that, and they really are smart people.
Oh,
Sometimes
that is exceptional. I thoroughly enjoyed that. I thank you so much.
Thank you, John. Can I ask something? How your opinions about? I've always been wondering about the Geminid meteors in December, and it's reputed to be the parent body is Phaethon. Now, I always wondered if it was an effete comet, because they call it an asteroid. Perhaps it is an asteroid.
Right.
Because that may be enhanced by the fact that many of the Geminid meteors are quite bright, so maybe bigger particles. How do you feel about that?
Okay, so first of all, are you winding me up here? Because Simon Green and I discovered Phaethon.
Yes, right. No, I didn't know that.
no.
I photographed it actually several years ago.
So if you remember, I started off by saying that my first job was to search the data from the infrared astronomical satellite, moving objects. Phaethon was the only near-Earth asteroid we found. We found 6 comets. I found the comets, Simon found Phaethon, but I always took the view that we were a team, and I always credited him with a co-discoverer of the comet. So I feel reasonably comfortable crediting myself as a co-discoverer of Phaethon. It was 1993 TB, it was called at the time. And within a day or two of its discovery, people had figured out that it had the same orbital elements as the Geminids. And I indeed subscribed originally to your view that it was probably an extinct comet.
Yes.
But over the years, I've kept an eye on this thing, on the literature. And over the years, it's become pretty clear that the thermal properties of this object are the properties of solid rock. They are not the properties of baked Alaska. I mean, that's the model, right, for an extinct comet. It's an icy core that's somehow got a crust over it that's sealed it up. And some years ago now, I can't remember how, 10, 12, 15 years ago now, maybe, some of the astronomers who do solar system work in Hawaii, Dave Jewett and so on, they got some data which showed dust coming off Phaethon at perihelion, so its closest point to the sun. So what's probably happening there is much the same as we're seeing with the Bennu thing, where it gets close to the sun, it gets very hot, and there's a lot of thermal stresses, and rocks just ping apart and throw off bits, and that would explain both the existence of the Geminid shower, and, as you say, the Geminid meteorites are known to be, or meteors are known to be particularly bright and persistent, which would suggest that they are indeed slightly larger than the typical stuff in a cometary dust trail, which is cigarette smoke. So we probably are looking at sand grains or something here. So
wow, that's fantastic, John, because I'd looked at the Geminids for many years and was very well aware there were many bright meteors. And of course, I just held that they all originated from comets, but just your talk tonight made me think about that. So it wasn't anything to do with your discovery. It was just the fact that you explained this, these particles coming from asteroids. And I thought, well, gosh, Phython must be an asteroid after all.
Yeah. Well, it's 1983 we found this thing, and about every 5 years, some journalist rediscovers the fact that it was discovered by somebody in Scotland, and BBC turned up and photographed me for a couple.
Oh, thank you for that.
Can I ask a question that's related to just what we're talking about? Has anybody ever analysed the spectrum of the light from a Geminid meteor fireball and come up with any conclusions as to what it's made of?
Don't know. I mean, it's
a
pretty tough thing to do, because they only, you've got to get on them and take the spectrum. I guess you do with a camera with a objective prism or something. But
Tom Lloyd Evans brothers did spectra of meteors.
Yeah, that's who I was thinking of, actually.
Yeah. I know Bill Ward, who's over on the West Coast, has been getting some fantastic meteor spectra as well. He's been publishing in the journals. I don't know if you obviously just have to wait and make the most of the bright fireballs you get. I don't know which particular showers he's been imaging, but he's actually some quite nice spectra where he's been able to identify some of the individual sort of elements and so on within the object.
Yeah, but it's an obvious thing to do. I mean, I'm not really completely au fait with that. Whenever I'm in the library, if I see the word Geminids in the journal article, I go and have a quick read of it to see what they've found. Seems like a long time ago now. I was quite young in 1982.
Yeah, I was going to ask on a related note again, that you think this is probably a common occurrence for asteroids to, especially the rubbly pile ones, to be throwing off bits and pieces?
Well, I mean, the other one, Ryugu, doesn't seem to do it. But the very fact, I mean, the chances of, it must be fairly common. Otherwise, the chances of you, either it's a 1 in a million chance you just happen to pick the right asteroid at the right day, or it fairly often happens. So it's not by any means impossible that it's happening quite often. And it does neatly explain the Phython Geminid issue, and possibly 1 or 2 other showers which don't seem to have parents. Most of them, of course, wouldn't produce meteor showers, because you only get the shower if the orbit of the asteroid exactly crosses the orbit of the Earth. So if it's even a few thousand kilometers off, the dust flies over the top of you or flies underneath you or something.
Yeah.
But it was an interesting discovery.
Yeah, a comment from Colin Steele on YouTube saying that the spectrum of a meteor also contains a lot of atmospheric elements, and it'd be difficult to sort out what is coming from the atmosphere and what is coming from the meteor.
I guess that's right, because it's a trail of ionized gas from the atmosphere, isn't it?
Yeah, so that's another complication to trying to do asteroid spectra. Meteors.
Yeah, I guess the Geminids don't actually produce meteorites, do they? They just produce meteors. What you really want is a meteorite, and you could pick it up and take it to the lab.
Yeah.
That again suggests that they're very small particles, because they don't survive to reach the ground.
I was wanting to ask John about the composition of these asteroids. It's interesting that they're both sort of similar rubble piles rather than solid objects in terms of them being potentially impactors on the Earth. What effect that would have on them coming through the atmosphere. I mean, I know that they're obviously traveling fast and the atmosphere is not that thick. So whether they would actually remain kind of coherent enough to still impact as a single object, or whether they would fragment as they came through, and whether that would have an effect on the area of the resulting impact.
I don't know is the answer. I mean, I suspect, as you say, that the atmosphere is only a few miles thick, and these things are half a mile across. I mean, the big ones, the front ends hit you before the back ends even got into the atmosphere. I suspect that even if they do break up, all the bits would land so close together there wouldn't be much difference between them fragmenting or not. But the converse is what happens if you try to deflect them, and that's one of the things we'll find out from this DART mission. I mean, in the extreme case, and I don't think it's very realistic, but if you may remember, there was another mission a few years ago to fire a copper dustbin at Comet Tempel 1, you know, one of the sort of 5% probabilities was that this piece of copper would just go in one side of the comet and come straight out the other, because it would just pass straight through it. Of course, that's not what happened in the end. But this is why we really need to understand the structure of these things. If we're seriously concerned about deflecting them, we really have to understand how they'll behave, if they're impacted, if they're exploded against, or if they can be maneuvered with gravity tractors or laser beams or something. And that's the justification behind DART. Now, I talked about DART to the Tweedale group, which is a local astronomy club just a few miles from here. And one of the chaps there said, well, sounds like a complete waste of money to me. To which my response was the stock response of asteroid astronomers. Yeah, that's what the dinosaurs didn't have an astronomy program, right? And look what happened to them.
Yeah, I think we've been probably lucky not to have had any really major impacts. I mean, if Tunguska had happened over a populated area, it would have been quite a different matter.
Yeah, and the one in Chelyabinsk a couple of years ago, the one over Russia, where almost all the casualties were caused by, as I understand it, almost all the casualties were caused by people who were looking through the windows when the windows imploded and they were all cut up by flying glass. But yeah, I mean, I cycle a bicycle in Edinburgh. Why would I be terrified of an asteroid impact, right? But at some point, integrated over the whole of the Earth's surface and integrated over a couple of thousand years, it's going to happen sooner or later. So we can't be too trivial about it.
John, asteroid sizes. We're thinking of asteroids that you've told us tonight being composed of really rubble, broken up perhaps many times. What about an asteroid of 3 or 4 or 5 kilometers diameter? Would there be any solid material below the surface of debris or rubble?
Well, there's clearly a continuum here. I mean, if you look at something like Ceres or Vesta, which are decent sized asteroids, are basically mini planets, and they look exactly like planets. They have crusts. They even have metal cores in many cases. So there's clearly going to be a smooth transition from objects which are just mini planets and these rubble pile type things. And I think it's the 2-hour spin period, I think, is what gives it away. Is that once you get above a certain size, you do find that they can spin quite quickly, but the small ones don't spin quickly, so they must be rubble piles. It's an interesting subject. I mean, like as I said, I mean, I grew up with the idea that asteroids were all made of rock and they were all big and chunky, and we now know that some main belt asteroids emit comet-like vapors, and we know that some near-Earth asteroids aren't solid at all. I mean, it's the other one. Almost all of the ones that have been targeted by spacecraft have had densities very close to 1, so they must be half holes and half rock to have such low densities. And the more you think about it, the solar system's been around for a long time. There's been a lot of collisions in the main belt, so it's not surprising really. But these things are easy to work out. It's always obvious after the fact, right? It's the same with the extrasolar planets. Who would have thought that almost all the extrasolar planets would be giant Jupiter things with an orbital period of 2 days? Until you found a few, and then you suddenly realized that, oh yeah, of course, obviously.
I suppose that has implications for the planned future asteroid mining operations, which people keep talking about. That it's one thing trying to mine minerals off a solid rocky surface, whereas trying to scrabble up things that are just dust and pebbles is needing a totally different technology.
Yeah, but of course, what you would do, I mean, first of all, you'd find an asteroid that was made of what you wanted. Remember, some of the asteroids are metallic asteroids, which are essentially just giant iron meteorites. They're the cores of exploded planets, and they're pretty much solid metal. So it's just going to pick the right asteroid.
I won't be investing my money in it yet.
No. All righty. I mean, I'm more than happy to chat, but I guess we're just about running out of chat. I've noticed that some of these Zooms, I've been to quite a lot with different societies, because of course you can do that. There's the Clydesdale group over towards Glasgow, and then the Edinburgh people often invite me to their Zooms as well. I did something to the Airdrie group a couple of weeks ago. You could spend half of your life on Zooms to astronomy clubs these days.
That's true.
But what I have noticed is that some people do sort of, they're going like for an hour and a half, and it's okay. I suppose you can just turn off your camera and go and watch the telly for a bit. But I didn't want to go on too long.
No, that's okay. There's no questions come up on YouTube, apart from Colin's comments on trying to get meteor spectra. So
okay, good. So I hope you get your observatory back soon, and perhaps in another year or so we can come up, because we came up to do something else for the Institute of Physics, which Brian organised a few years ago, and had a really nice evening. We're looking forward to coming up again and doing a bit of exploring around your part of the country. My son was at Dundee University, actually, so we used to come to Dundee quite a bit, but we haven't been up for several years now. So perhaps another year or two. I think I put together, at the risk of walking into putting my foot on a mine here, the thing I put together for Airdrie was space exploration as told through Airfix model kits. So if you ever fancy talk about space exploration and plastic model kits, I've got
really about that in a year or two, maybe.
Talk already prepared.
That'd be excellent.
That'd be brilliant. Yeah. Well, you are more than welcome up here at any time you're in the area. We're desperately hoping that we're back, face to face, being able to chat and discuss things come the start of the season in October. Because I mean, apart from the blooming pandemic, we've had one storm after another storm, which brought down all the trees going up Balgay Hill and closed the access road. So it's just been a bit of a disaster this year. And hopefully we will all be back together again in October, which would be really nice.
Yeah, I mean, lots of. I mean, the Tweedale group is exactly the same. We've been kind of hoping we could get back to face-to-face meetings, but there's just too much uncertainty. I mean, leaving aside the political situation, I mean, there's just too much uncertainty with COVID, because many of the people who come to meetings like this are vulnerable to some degree or other. So we're not in too much of a hurry to go cram ourselves into a room. But I agree with you. I think hopefully by the summer things should be back to more or less back to normal.
I'm very much hoping. I think that you're quite right, but vulnerability is a major issue, and at the moment, rates are high, but maybe soon it would be good. It's not, I mean, Zoom's been marvelous because, we've been able to get talks like yours, and this is terrific, but we really miss the discussion bits where you get to chat to other people with an interest, and it's so hard on Zoom to mimic that. You really have to be in the room.
Yes, one thing which I've suggested that the Tweedale group do, I don't know if you do it, but I've suggested we form a group and all do the same Galaxy Zoo experiment. So this Galaxy Zoo is citizen science thing, and I've suggested everyone who's interested all does the same Galaxy Zoo project, which is the Planet 9 one. And then when we do get together, we'll all have at least something in common. Have you tried this? Or did you find anything? Yeah, what was your biggest problem? So I'm trying to get a Galaxy Zoo campaign organized through the Tweedale group.
Well, that sounds quite exciting. Yeah, absolutely. And that's exactly the thing, is to have something that brings everybody together and keeps all the enthusiasm going. And it's just impossible, I think, on Zoom to get that type of interaction. But well, it's bound to get better, isn't it? It's just bound to get better.
Yeah,
So we'll give it.
I can't say I've enjoyed the last 2 years very much.
No.
No, it's been horrible. Just horrible.
Okay.
I mean, we thank you incredibly for, that's just the most fascinating topic, which I certainly, I'm still kind of coping with the engineering of it and the clarity of it, but that was brilliant. So we thank you very, very much for coming and telling us that. Super talk, John. Absolutely super.
Thanks very much.
Thanks a lot. Yeah, hopefully we'll see you in person next time.
Yeah, let's hope so.
Thanks very much.
Bye.